Wait, I need to get some photo.
If we
So I will share now, okay?
Mhm. Wait,
No,
wait,
no, 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 yeah, I need to see, yeah. 3D model maybe after.
3D.
So which one is the programming connector you want?
This J something like J.
Oh, okay, okay. Can you take those out somehow? It's okay. Getting side also okay if it is not interfere in the solar panel.
Mhm.
No need to worry. Like it doesn't matter. I like this method before than our system.
Because you put on top of the. It's
Okay.
like
Now I will show. Okay.
okay, okay. I cancel mine.
Uh, okay. Now can you see?
Yes.
So you can see here we connected wire from back side. Actually bottom.
Mhm.
So actually no need to worry because wait I need to find a. We had another connect other side. Another hole. I need to find that. This is our programming board actually. You can see you can connect different packages.
Mhm.
I hope
This is birds.
I iPhone. There's a test going. That's why there are so many photos. It's the same photo. I need to find. Anyway, I will explain. There is access port here also
Mhm.
sideways.
Sideways.
Yeah, it's okay if you can manage it. It doesn't matter. So basically, if the vibration test and those things okay, so then no issue
So
actually.
that side what kind of connection you put? What's
So
what
the
is
problem
the
is when you put somewhere here, it can interfere the solar panel. You can see solar panels are in this side, so you have to place the solar panel correctly.
Mhm.
So let's say if you accidentally place the connector somewhere here, you will face a problem because you it's very hard to place solar panel four solar panel in one side if you do that one.
Mhm.
So you have to place it somewhere like this or some in between here, and we can move the solar panel a little bit this direction.
Mhm. So for the sideway
It's okay
interface, what
because you are not going to connect anything when it is inside the deployer. So these are the deployment switch. You can see small here. This
uh-huh.
places. So those must be there. Okay.
Okay. So what is the RBF remove
RBF.
before?
Okay. 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 Maybe I need to show. Here you can see we have holes here.
Mm.
So one of RBF is there, other one was removed. So this was actually ground disconnection RBF. So we had to take it out when we measure the battery voltage inside the satellite. So satellite is not on right now. Basically, we are measuring the battery voltage. So that's what happening.
Mhm.
So it doesn't matter which side you are connected. Wait, okay, I need to show maybe some photos or another photos. Okay. This photo is much clear. Here, can you see here? This is one of access port.
Access port.
Access port, yeah. So you can see the solar panel almost touching there. So that hole. So you have to place it correctly, okay?
Mm-hmm.
So maybe okay. So this is the backside access bottom
Mm-hmm.
actually.
This is including the RBF.
Yeah, there are RBF pin. So the problem is you one more thing. You must move the RBF to this direction. Okay, sideways is not possible.
Oh, need to modify also the board.
Yeah, but please read the specification. Okay.
Because I saw from the specification. Let me share. Okay.
Okay. Okay.
Mm. This part to you Cubesat
Yeah.
specification. It mentioned that you have to put your access port that way.
Okay.
So what this actually means? Because I saw that you put at the back, right?
Yeah. Yeah. Actually, one more thing. I was not a structure guy, so I'm not sure why the structure wanted to place it there.
Mm-hmm.
So I'll ask and tell you. Okay.
Because this is the CubeSat specification design from Cali, Cali,
So
California Polytech.
okay, 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 that's correct. But what is the launcher you are going to use?
Huh? Sorry?
What launcher you are going to use?
This one actually we only designed for made for training.
Okay. Okay. Then
Uh,
no need to worry.
so
Just follow the California design.
so we don't we still experimenting. So
Yeah, yeah, it's better. So it's okay. Just follow that system. So if you get familiar with this bus system, those electronics, then
uh-huh.
later you can change it according to the launcher requirement.
No launcher requirement.
Yeah. Okay. It's okay.
Uh,
No need to
so,
worry like that.
if possible, also please ask and
Okay.
inform about
Yeah,
the.
actually that's good because I'm also thinking why is at this backside.
Mhm.
So I need to ask. Okay.
Okay.
Okay. Uh, so can I start now? So I will start now. Okay.
Okay.
Uh, maybe wait. That is not the correct screen. I will quickly explain the OBC remaining part and go to the those programming. Okay. So as I told last time, we have the config here and we have the main pick here. So config had its own flash memory. There is a UART line going to the main pick, and there's another UART line going to the reset pick. Okay, from config. This main pick has a FAB UART line, and it has where it goes reset pick, and it goes to config. And here we have the shared flash memory in between com and uh, main pick. So it's simple multiplexer. I'll draw and show. Okay, the way it's connected is like this. So we have the main pick, and we have the home pick, and we have a multiplexer here. Okay. So flash memory. So we have MOSI, MISO, and clock, chip select. Okay. And so it's connected like this. There is a control line coming from main pick to this multiplexer. If this line is 1, this this flash memory will be switches to this direction. Okay. Basically, all the line will be switched to this direction. If this one 0, all the line will be switched to this direction. So that's how the access happen. Okay. So you have to remember this multiplexer is controlled by main pick. Okay, not the compig. Compig don't have the controllability. Anytime if compig need to access data, you need to request from the. You have to tell to the main pick through this UART line. I'm going to access. Normally, so main pick keep the access to this direction. Okay. So sometimes don't need compig no need to tell to main pick I need the access. But the thing is, if main pick is doing something with this flash memory, compig don't have the access in this part. So it's always good if compig can tell to the main pick, please give the access. So that's how it happens. Okay, in the programming you can do that one. Okay, so it's very simple. So basically you need to send some messages and main pick will send the acknowledgement after giving the access. Okay, then it's very simple. It's here. Okay, and similar to that one, as you remember here, there is another flash memory. It goes to the outside of the OBC for 2 missions. Okay, from main pick to missions. So any other board external to this OBC can access this SPI port, and then through that SPI port they can communicate with this flash memory. So this is it. Okay, so you can see, so it's connected to the flash memory, again the multiplexer, and through the multiplexer. Last time it was compig here in the other side, this time it's something else. Okay, it's going to outside. And one more thing, main pick has its own flash memory, as I this one. Okay, flash memory 0. So it's connected here. You can, if you see, if you check these things, you will understand. Okay, so the OBC person needs to know every line. Okay, where those things going and why those things are. So these are buffers. So you can see the FAB UART line and everything you need to know. And what are the empty DIO lines? What are the used DIO lines? It's better if you can put some notes here. Okay. And one more thing here, there is in the block diagram I explained there is a hardware UART line goes to outside to access the main PIC. Okay. So access or debugging. So we don't use PIC it to debug. So we use this UART line for debugging. Okay. So anything happened inside the main PIC, it will print outside using external serial reader. We can see what's going inside this one. Okay, I will show an example after this one. Okay, when I explain the reset PIC. So you need to remember something here. Normally, UART is TTL in PIC IC. So voltage vary from 0 to 3.3 volt. So but there's a problem in this path. Okay, in the initial design, this side is TTL. If you use normal serial reader, you have to connect here to this line, RxTX line. Maybe I'm not sure. Wait. Maybe this one TX, maybe this one RX. Okay, it can be changed, different. Okay, but basically it's TX and RX lines. So using this converter, it converts to that plus minus 6 volt signal. So if we have this kind of chip, we can send this UART little bit longer. So in that case, we cannot use this TTL reader. TTL reader will get damaged if you connect here. So you have to use a different serial reader. It has plus minus voltage handling. Okay, so data goes like this in this UART line. So the thing is, in the after bus 3, no, after Kitsune, we take out this one. Now this line directly comes out using any serial reader, normal TTL reader, you can access. Okay, so did you use this port for anything?
We follow same schematic.
Yeah,
Bus 3.
so you did not turn on the board yet.
Oh no, not yet. Turn on.
So can I give one suggestion?
Uh-huh.
So do you have any guy who can do better soldering?
I can do so.
Okay, can you please take out this chip in the board and
Mm-hmm.
connect this directly to external?
Oh, just connect to the direct to the
Direct. So
UITX.
then you will not face this issue. Otherwise, it will be so hard. You need to buy that serial reader. It's a
Oh,
different one. So if you connect the normal serial reader, this voltage will destroy it because it has negative 6 volt also. It happens many times. People did not know it's connected.
yeah, this one to connect to uh, the uh, sorry, this one actually need to connect
Basically,
to the computer PC.
this basically goes to the FAB. Through
Maybe.
FAB,
Uh-huh.
you need to you need to connect it to serial reader, and serial reader will be connected to PC. But this voltage is little weird. Not weird. You have to find a dedicated serial reader.
So I connect this to like the
Okay, I'll show.
UART to
uh,
USB converter to
Can you
PC.
do this one? This one, and then
Or out.
this one.
Mm-hmm.
So then you can use any serial reader, normal TTL reader, serial reader.
Mm-hmm. See.
Okay.
Okay.
Uh, one more suggestion. If if you can, I don't think you will be. It will be easy. Please put a 100 ohm resistor, okay?
Uh-huh.
Somewhere here, somewhere in this line series. So I think you can do it somewhere here, okay?
Mm-hmm.
Maybe to 100 ohm resistor, 100 ohm resistor. You can do it using a resistor.
Mm-hmm.
Because the reason is, if someone accidentally connects something here wrong, like let's say someone accidentally connected some 3.3 or some 5 volt here.
Mm-hmm.
Since nothing here, if you don't have this resistor, it will directly go to the PIC IC.
Okay.
So it can damage the circuit, okay?
Mm. Yeah.
So you can see any line goes outside. So from flash memory also you can see it has some resistor added.
Mm.
So that one also, okay?
Yes.
And one more thing, very special thing, okay? Do you make notes or I can, should I send this one? Can it?
We record this
Okay, okay.
presentation.
And one more thing. So we have here, so this is RTC clock line, that is that 32.068 hertz line is coming from near reset pin. It goes to this buffer. From buffer, it comes to this peak. Okay. So there was a mistake. Actually, there's a mistake here. This RTC should not connect to this pin. It should be connected to here. I don't think you can connect this one, but I managed to connect it here in the first board. Okay,
Mm.
any RTC inside this pin will not. If you connect it to here, it must be connected to number 30. Okay,
Uh-huh.
so it was a mistake. So you need to cut this one and then need to create a new connection to here.
I see.
So it was a mistake in the first initial design. So I will erase this line.
Mm.
If you are late, like if you can do a small soldering, maybe you can cut this line and connect it to other pin. Remember, no short circuit in between number 29 and 30. Okay, when you do it.
No, it's just a kid.
Okay.
Okay.
So I think that's it for the OBC explanation. Maybe I think I explained here. So let's go for the reset pick. The way you turn on this board, okay? I will explain it. So
That that crystal actually wrong connection, right? There's a
yeah, it's connected to
operation.
the wrong place. It
Okay.
should be connected to 30, number 30.
30. 31. Eh? 30,
Yeah,
30.
it's 30, I think. It's 30, like this.
30, yes.
So it's 29, it's 30.
Okay.
So the confusion came because in the initial design, so you can see here it says SOS clock input or something. The initial design we made a mistake. We were thinking it should be coming here, but when we get the board we try to program, but it was not tenable. Then we read the data sheet. It says this one actually. SLK So shell to connect here. Then we
Mhm.
corrected, it works, okay? Otherwise, you cannot use any real-time clock here because real-time clock needs this input.
Mhm. Alright.
Okay. So then we can go to the reset pick. So if you remember reset pick, it has the power lines, controls, and then it has ADC readings, basically measure current. It has its own external watchdog timer, so it has to manage that pin also. And then, so these are the tasks of the reset pin. Need to control power lines, and then need to measure current consumption, and then need to manage its on the watchdog timer, and need to monitor config and main pick. Okay, so in your code, this thing should be implemented. It must be implemented. Okay, so now we have the reset pick, and we have the main pick, and config. That's a UART line in this part. And there's a UART line in this part. So every 90 seconds, main pick communicates with reset pick. When this happens, reset pick has to check the power line status, and it has to measure the current and do everything, and need to send the housekeeping data to main pick. Okay, this happens every 90 seconds. In the same time, with some delay, again 90-second frequency, compig communicate with the reset pick. It's just communication. Okay, compig don't wait, ask for any data. Just compig tell to reset pick, I am working fine. Okay, basically previous case also, that request also, reset pick think main pick working fine. Okay, let's say
Sorry, you mean every 90 seconds, the housekeeping data will be sent every 90 seconds automatically.
reset pick will not send automatically.
Then
Main
for
pick,
config, for
main
config,
pick, no, main pick will request, okay?
main pick will not request.
No, main pick will request.
Oh, will request. Why not? Why not send every 90 seconds automatically? Don't
The problem is this
request.
one. So I said reset pick need to monitor these things are working correctly. So this request is used as a monitoring function also, okay?
Okay.
If there are no requests to reset pick from main pick things, reset pick things or something going on in this main pick, so I have to do something like that, okay?
Okay, it means that like response also monitoring the main pick.
Yeah. Request also monitoring has the monitoring function.
I see. Okay. Thank you.
So
Then how
that
about config? Just now you say config.
config don't need anything actually. If you want, you can request something from reset pick, but config is a pick. It's just for the manage transceive, okay? TRX.
Okay, manage a transceiver.
Yeah.
Mm.
So it don't manage any data. It don't get any housekeeping or nothing. Okay. That housekeeping management done by main pick.
But reset pick control the power to config, right?
Yeah. Okay. In our code, let's say config correctly working. Every 90 seconds, let's send something to here. Okay. Which means reset pick knows config working fine. If main pick don't send any request more than 10-minute time, reset ping things. Okay, now something went wrong in the main pick. Reset pick will turn off the main pick and keep some time and turn on again. Basically, it's resetting the main pick.
Mm.
Okay,
Mm. Okay.
that's very important function you must have. Let's say you turned on some mission, something went wrong in the main pick and it got stuck somewhere in the code. So entire satellite will be like you will send any ground station command, it goes to main pick, but it main pick don't respond because it got stuck. So
Mm.
reset pick will monitor that kind of situation. Okay.
Mm.
So this 10-minute case you can change. Let's say if you think like okay, if within 5 minutes if main pick don't reply, no, not replies, if main pick don't send any request, which means main pick has a problem. Same for the com pick also. Okay,
Mm.
so that's very important. That's why I said reset pick is one of most important pick here. So it check everything.
Mm.
Even let's say you have the that OCP line is as example, let's say 3.3 volt line.
Mm.
If you know it consume like 1 ampere, if accidentally 2 ampere or something goes in that line,
Mm.
you can write a function. Okay, disable that 3.3 line to avoid the battery drain. Okay,
Mm.
basically you can put many protection function inside the reset pick. But you must check everything properly. You have to introduce errors to satellite. And the way we check this one is we intentionally make a problem inside the main pick or intentionally make a problem inside the com pick. So then after 10 minutes, reset pick will reset the both. Okay. So one more function reset pick has to manage is keep the time. Keep the time. So reset pick will have the satellite time. It's like right now In Sri Lanka, time is so today is 25th. Right now, 8:45 or something. 8:45. So if you send a command to update the time, reset pick will get this time. So when you download data, reset housekeeping data, reset pick will have this timestamp in every data set. So you can see when at what time reset pick recorded the data. Okay. Normally we set the main ground station time. If we operate the, let's say, Qtech burst satellite or Kitsune, we send the Japanese time. So we know exactly what time satellite got the reading. It doesn't matter satellite wherever in the orbit, it doesn't matter. So we know what time it got the reading. And then if we need to see where was the satellite, using TLE or some software, you can see where was it. So it's very important to have time inside. Okay. So as I told last time, we have a software UART line here and hardware UART, and here hardware UART. Actually, not the line, the place we connect is hardware and software. Okay, this one is soft. So actually, in the Kitsune and Spartium, we swept these two lines. So main pick is connected to hardware, config connected to software, because this is one of most important connection. So it's, if you have a better hardware line, every time when the main pick sends something, this reset pick can capture it properly. So that's why we switch swap. But even with this connection, the code is written to capture it properly. Okay. So if you have any question, you can ask. One more thing, we have two interrupt functions here. In the reset pick, we have timer one interrupt. The second one is UART interrupt. So there are two interrupts inside the reset pick. So I will explain how it is done inside the reset pick. So okay, let's go to the code. Okay.
Okay.
So okay, it's not shared. Wait. I will try to explain this one simply, but little complicated, but it's okay. Anyway. It's not so long code, so that's because of that one I can explain easily. Can you see the screen clearly? Can you see it?
Yes, yes.
Okay, okay. So let's start from the beginning. So we have the here we include our IC and fuses. We are not going to use internal watchdog timer. We need to master clear function in that master clear pin, because we use external watchdog timer. Because of that one we need it. So no brownout, which means there is a timer for the low voltage detection, so it is disabled. And we need ADC reading function. So our ADC reading will have 12 bits. Okay, that's what it says here. Okay, 12 bits ADC, and the crystal is 16 megahertz. And then I created here a file which contains some registers inside this PIC. So sometime I have to use, normally in this compiler you don't need to use this register definition. If required only, I kept it there. Okay, then if you go here, so first I included reset PIC setting C file. You can see in here, if we go here, it has all the definition, those settings and everything added here. I will go here and explain those things later. And then I have reset PIC ADC function. So if you go inside here, it has the reset ADC measurement functions, and then reset PIC function. So there are some calculation function which is used inside the reset PIC. Those are included inside this one. So if you go there, there are things. Okay, so I'll explain those later. And then I have the function related to communication between reset PIC and main PIC. So any communication between reset PIC and main PIC, which those functions are inside this C file. So if you go here, you can find here the communication function between reset PIC and main PIC. And then I have here communication function between COM-PIC and reset PIC. It is not huge file, so it's very simple. So now you can see it's not hard. Everything properly organized. I don't think this one is there. This way is there in the burst 3 code. So you can go every tab and get it. Okay. Then I said I have 2 interrupts. Okay. One is timer 1 interrupt. Other one is UART interrupt. So using this line, I can prioritize which interrupt is the priority. So the most priority interrupt is this timer 1 interrupt. So it manages the reset PIC time. So I have to make it priority. And then UART interrupt is the next priority. So int RDA means UART interrupt. Okay. So interrupt priority, I'll put another comment here. Timer 1 interrupt, comma, hardware interrupt. So software interrupt cannot use any interrupt. Okay, no. So software UART cannot have any interrupt. So you need to remember that.
So this interrupt, you can just set its priority based on the sequence.
Sequence or
Like
the problem is, let's say same time both the interrupt happens. Same time. So you need to prioritize which one to execute, because 2 interrupt cannot be executed same time.
okay.
So the reason I had to make this timer 1 interrupt is, let's say this timer 1 interrupt happens every 1 second. Okay, if you ignore at least one time this timer 1 interrupt and execute the UART interrupt, so you will lose 1 second in the satellite. it's okay to lose 1 UART communication between the main peak or config, not the timing. Okay.
Okay.
So actually, this thing will never happen. So to run this, prior like happening cases, probability is very low because this time one interrupt execution time is like 50 microsecond. So this one is like 1000 microsecond. So like out of 1000, not 1000 even, it's very less chance to happen together. So here I have the timer one interrupt loop. Okay, so I will not directly go to this one now. So let's see some simple function, then with time I will go here and explain. Okay, then first thing I wrote this function a little bit different. Okay, normally we have the main loop and then a while loop, and it happens like that. So if you are familiar with Arduino, you have a setting loop. So I just, similar to Arduino, I just created a function called setting function, and I call it inside the main loop. So it's very simple. Okay. So the code runs starting from here and goes inside, and inside the while loop it will keep happening like this. So the first function run is settings. Okay, let's go inside the settings. When you turn on the peak, so it will print boot in reset peak in the debug line. Actually, for this debugging, I use the programming pin. So because from reset peak, you have the PGC line coming outside. If you connect serial read receive pin to that pin, you can read the reset peak serial. Okay, did you understand? Maybe I'll draw and show. Okay, so we have the OBC board and we have the FAB. So FAB have external PGC and PGD line. Those lines through this one and through the backplane goes to the main peak and reset peak and config. So it's connected to all the peaks. Okay. So this is main, this is reset, this is comp, and then you have the PGC line. This again goes to the every peak. So when you program, the programming will happen through this one. After that, you can take out the programmer from here, and from reset peak, you can send back the UART line through this one to outside. So that's how we access. Okay, the whatever sent here will go to this direction also, but we cannot do anything because that's how it connected. So you have to remember, you must not enable. If you enable this as TX pin, you must not enable any of these TX pins. Okay, main peak, you have your dedicated debugging line, but for the reset peak and config, we have to use this PGC and PGD. Okay, that's how it happens. And then first thing after that one, I set the time. So as example, this is 2024, and then March 23. Time is 3:45. Depending on your requirement, you can set the required time. Okay, understand? Any question until now? No issue?
no.
Yeah, basically this function is very simple. If you go inside this reset pick function, where is that? So here, set reset pick time. So I just load my required values inside variable inside the reset pick. Reset pick has its own year, month, day, hour, minute, second variables. So I just update those values using that function. It's very simple. Okay, and then we have to enable the interrupts. First, I need to enable the interrupt one. Okay, no, timer interrupt. So actually, so you can see the comment: enable timer one interrupt. Then enable UART interrupt here. Okay, and then enable global. So even though you enable those interrupt, you need to run this function to start processing. Okay, otherwise nothing will happen. Okay, so these are recommended by this compiler. Okay, then I need to get 1 second timer interrupt using the timer one. So if you get 1 second timer interrupt, so you can create your own RTC. Okay, this PIC don't have an internal module to create have time. So the main PIC actually has an internal module. So you just need to give the external that 32 768 clock only. So basically it has month system, like minute system, hour system, but we don't have in this in PIC. So we have to create by ourselves. Okay, so the way we enable the timer one, so first we need to tell this line, and we need to tell which timer we are going to use. There are timer 0, there are timer 2, but we are going to use timer 1. And then so that this is prescaler, and then if we run this line, it will enable the timer, and then timer value we have to load. Okay, this is how it is done. So I'll show the equation we use to get this timer delay. The equation is required interrupt duration is equal timer max value minus timer value we loaded, and then divided it by prescaler and multiplied it by the clock we provide. So this timer one is a 16-bit timer. So which means the maximum value of the 16-bit is 65,535. Then we need to load our value here, 32,767. 32,767. and divided by our prescaler is 1, and we need to put our clock source 32, 7, 6, 8. So then we will, so if you see, these two values will give the same actually. So we can cut here. So you will get 1 second timer interrupt. Okay. Using 1 second, let's say every 1 second this interrupt will happen. You can increase the second. 1, 2, 3, 4. When it's reached to 60, which means 1 minute pass, you can increase the minute variable. When the minute goes to 60, you can increase the hour variable. When the hour variable goes to 24, you can increase a 1 day. If it is 365, it's a year. So that's how we manage the time inside the receptacle. That's a simple function. Okay, then we need ADC. Almost all the actually not all analog ports. How many? No. So this is first. When we enable the ADC, you have to tell which clock source we are going to use. For the ADC, you don't need a very accurate clock source. You just need only very fast clock source. So because of that, we are going to use ADC internal. So it will use the crystal which is connected to a receptacle. Okay, that's 16 megahertz one. That clock will be used to convert the ADC values. So then we need to tell what are the pins we use for the ADC. So the way it says like this, so you have to put S and AN0, AN1, AN2. Actually, this is O. So if you have something else, you just need to do this one and put, okay. So if you go to OBC here, so the lines we used, you can see here, AN5, AN4, and then AN3, AN2, AN1, AN0. Those things are used for the used as the ADC. So AN0, AN1, AN2, AN3, AN4, AN5. So then, okay, then it is enabled. So then we have the function to turn on the different power lines. So it's very simple. If we turn on the main peak, so there's a function called main peak power. These things are not in burst 3, okay? It's kind of confusing when you say it. And then if you want to turn on, you put on. So you can see here, just if you want to turn off, you just put off there. So it's very simple. And config on, similar to 3.3 on, 3.32 on, and 5 is line on or off. So unreg, actually one more thing, you need to put this one off if it is in the real case. Okay, normal. This unreg one is connected to transceiver. Okay, transceiver line should be off when you turn on the satellite for 30 minutes. Okay, that is the real case. I will explain that one. So you know, in ISS, let's say satellite, this is ISS, and satellite was released. There is a requirement. Oh, sorry. Cannot see it. So this is ISS. Can you see my screen? Can you see it?
Yes.
Okay. So we have ISS. When we release the satellite, ISS has a requirement saying until 30-minute finish from deployment, please don't transmit any signal. So you have to wait 30 minutes to turn on the transceiver. So which means when the satellite is deployed, transceiver should be off. So that's why I have to turn off the rig one line. But in your testing, you don't need to do this condition. Otherwise, you have to wait. Every time you have to wait 30 minutes when you turn on the satellite. So just go with on, okay? All the power lines are on. Okay. So this function, you can find this one, reset bit function. If you go here, I have put which line enable which power lines, okay? You know, which pins enable which power line, okay? So if you go, you have to check the schematic. Please have a printed schematic when you program or different screen in your computer, okay? I put here which power line. So C4 pins enable 3, actually this 3.3, okay? So since this is spartium did not have this kind of 3.31, it had 3.3 and 4.5. So that's why it says 3V3 2. Okay, so OCP enable and what is this? Buck enable and OCP enable 5 volt OC buck enable OCP enable, and then unreg 1 enable, unreg 2 enable line, and config power enable, main pick power enable, watchdog reset pin, and row voltage monitor enable. Okay, those are the pins. The way this function run is like this. So let's see how this 3.3 one line control happens. Okay, void 3v31 line. So you have to put the on or off, and then actually if you go here, I have defined on as 0 1, off as 0 0. So that's why if I go here, instead of 1, I can just put okay, it doesn't matter. If it is on, output high pin D1, and I little bit delay to enable. First I enable the buck boost converter using this one. Before enabling the OCP, I little bit delay, okay? It's better a little bit delay. And that's it actually. So it will turn on. To turn off, else both will be low. Okay. Understand this function? Did you understand? If you don't understand, please tell me. Is it okay? Someone please give me back feedback, because I'm same time. Okay.
I think it's okay.
Okay.
Mm.
So there's something else here. This is one of very important line I put. Is it like this? So we have one variable called power line status. Line status. Okay. So this variable is an 8-bit variable. So I'll write it using binary. Okay. 0 0 0 0. This is by okay. There will be confusion happen if you do. Okay, like this. So if you take 8-bit variable, it has 8 bits. So if I turn on the 3.3 line, what I do here is I make this bit 1. So I use this one for the 3v3-1. So if I turn on the 3.31 line, I make it 1. If I turn off, I make it 0. Okay. If I turn on the 3.3 line 2, 3v3, 2, I will, so here 7, 6, 5. These are bit numbers. Okay. 4, 3, 2, 1, 0. And if I turn on 3v3 2, I'll make it this one 1, and then 5-volt line here, and I don't actually remember whether this is a main pick or config. When we see, we can confirm. And now I made a mistake here. This is unreg 1, unreg 2. Just get the idea. So this thing order can be different. Okay, maybe those things are main pick or config. Okay. So every time if I do some changes to those power line, I will edit these bits. Okay. Let's say after some time you have something like this. So if you check this variable, you know 3v3 line 1 on, 3v3 line 2 on, 5-volt line on, unreg 1 line is off, unreg 2 is on, main pick on, config on. Okay. So you remember main pick every time request the housekeeping data from reset pick in every 90 seconds. With that housekeeping data, reset pick will send back this variable value also. Okay. When you download this data, you can see this variable value for different time. So you can see which power line was on or off. Okay. Using this register value, we can see which power lines are on or off. Okay. That's why the variable name is called as power line status. Okay. Did you understand?
Yes, understand.
So this is very important variable. Okay. Sometime if there is an error, you can see which power line was running when you download housekeeping data. Okay.
So how
You
how
mean
to
if there's
say
okay, sorry. If there's
Okay.
an error, how it's review the error,
Oh.
like let's say the example, if I say error, then if how do we detect from the housekeeping data? You mean
Okay.
that, yeah.
Let's say power line status, let's say 3.3 line is off. Okay. 3.3 line off according to the reset pick. Let's say like that. But there is a current in 3.3 line, which means some hardware damage in the OBC. Without there is no control to the reset pick. Power line is always on because of something like that. Okay. Understand? It's like this. Okay?
Yeah, understand. Yeah.
Yeah. Like it's your basically you can see what was going in the satellite, what line was on, which one is not on. sometime it has happened. Actually, this value is 0, but 3.3 line has a current. So actually it happened because one enable line was short circuited to the high. So because of that, 3.3 line was on. Even reset peak did not turn on, but line was on. So we could find the problem like that. Okay.
Okay.
So then we have the 3.3 line 2. So you can see using this bit set function, I can set the which bit, a given bit. Okay. So you can see here the fifth bit is set for the 3.32, and 5 line is the fourth bit here, and then unreg 1 is it third bit, and so you can see here bit set, if it is on, otherwise it's bit clear. Okay. And then unreg 2 is the second, and config is the first, and the main pick is the 0. So I will show some housekeeping data, how this is used. Okay. Then you can get the idea how it's happening.
All right. Thank you.
Please give me a few seconds. I need to open the illumination equipment. Illumination test. This. Okay. This is one of long duration test of Kitsune. Okay. Basically, you just need to download data. So you can see here is the data. It's easier sometimes using Excel file to see the housekeeping data. Okay. Then just download the data and put inside this box, and then it will extract different sets. So you can see here, so the extracted data, you can see here at what time it was recorded. So as example, 2021 February 23 at 12:06 is the minute, second is the seconds. Okay. So you can see, and then what was the raw voltage and the 3.5 line current, and then 4.5 line current, 5 volt line current, and those, and then you can see which power line was on. Here you can see, using that variable you can tell, we calculate on the ground. Okay. So these are very important when you can then plot those values and see. Actually, this one was one of TVT data, thermal vacuum test. So you can anything.
Oh, what I mean is the green on our right hand side, if I say they are also confirmed there is no data for the reading for their power line, is it? Let's say UN2 line is off, but still got but I can
This
see
one, this one.
I thought that the green
Okay.
green
This one?
color, yeah.
Yeah. UN2 line is off, but you can see something. This is the thing is, when you calibrate that plot has the ADC reading always has an error. Okay.
Okay.
Like I will actually, so when you calibrate, what you do is, so you plot the current value here and voltage reading, some ADC reading, okay? So you will get some values like this. It's not so linear, but it's not, it is little wrong. And then what you do is get the average graph like this somewhere. So in the beginning, it little bit goes to negative or some positive. It will not exactly go through the zero, okay?
Okay.
So we know, okay, if we see something like this, we know that is zero, okay?
Meaning 0 and negative 2.3, they are same. It's off.
Yeah, it's same.
Then go lower than negative 2.3, negative 4.7, I can see also means off lah. Okay.
Yeah, like it can vary, like.
Yeah, okay.
So if we see like negative 10, something is
Confirm
wrong.
off.
Yeah, we have given like 5 milliampere error plus minus.
Oh, okay.
You cannot exactly measure. Sometimes even because of small noise, 1 bit can flip easily.
1 bit can what? Sorry?
It's like this, okay? Okay, wait.
Okay.
So let's say you use 8-bit ADC.
Yeah.
So it vary from 0 to 255, okay? So let's say if you measure a small voltage, maybe that ADC value is 5 or something, okay? It can be 6 or it can be 4 because of noise. That error can happen even in your reading. So you have to understand there is a error always, okay?
Okay.
The thing is, you have to minimize that error and you have to accept whether it's okay or not. Let's say a 20 milliampere error. Oh, okay, that is not okay. So you have to do something for that one. That's too much. Okay, like that.
Okay.
So,
To do something.
so you have to do the calibration. Okay, I'll show. It's better. I'll show one more burst X calibration. Okay.
Okay.
So this maybe I show 3.3. This current sensor 3.31 current sensor calibration. Okay.
Okay.
Testing. Oh, this is panel. Set pick. So you can see here one calibration. What we did was we get some current output and then get the ADC reading here. So and then plot it. Here you can see the plot we got. Okay. I think this axis is current. This is the ADC reading axis. Okay.
Okay.
So if it is perfect linear, not perfect, like if it is okay, you can see what's the problem here. If you go here, it's not exactly started from 0. Little bit has a error. So that's why we get something like that. If it is perfectly proportional, you should get a y equal mx type equation. But you can see it's not y equal mx. So it's y equal mx minus c.
Yeah.
So when the x is 0, you have 6.2 error.
Yeah.
So that's why we have error. Okay. If you know this one, If you know,
Mm.
then it's okay.
It's
If you
easy.
know whether there is error, then you are okay. Let's say if you don't know there is a error, that is a problem. Okay. And then unreg one line calibration. So there is an issue in that line. So after some time you cannot measure the current. It will start to drop.
This
So
become unlinear, right?
yeah.
Yeah.
After 1.6, no, after 1.5 ampere, it cannot do it. Okay. So we know after that one is not linear, it's a weird function. In an unreg 1 and unreg 2, you don't need exact current reading because those things are used for burner circuit and the transceiver. Transceiver has its own things, so no need to worry about that thing. So then the main peak power line, and okay, so I explained this timing. Then there is, okay, that's it. Okay, so then I go inside the this main function. Then we have the infinite while loop. While loop ends here. Okay, and then the first thing I see is I have something called main loop counter. This will increase every time when the main loop runs. Okay, if main loop run one time, this become 1, second time this become 2, third time this become 3. It's like that. Okay,
Okay.
so with everything main loop will take some time. Okay, from here to here there will be some small microsecond delay will happen. Okay, so which means when the to reach this, let's say as example, this main loop reached to some value, let's say it reached to 1000, which means some time has passed. We don't know how much time. Okay, did you understand that one?
So far, I understand.
Yeah, okay. So if you know, if you can measure how much time take this counter to reach 1000, you can create some not so accurate timer. Okay, I found out when the counter reaches to 4000, it's about 100 millisecond delay. Understand?
You mean the count? This program shows
Okay,
count.
one more thing. Forget about every function here. Okay, those things are just running. Okay.
Okay. Okay.
So when the this loop runs, this counter increases.
Yeah.
One loop takes some time. Okay.
Hmm.
See, so if counter is to 4000, I found it is about 100 millisecond. It takes about 100 millisecond to reach 4000. Okay.
Okay. Meaning it's already become a fact that 4000 takes about 100 milliseconds, or you have gone through the research.
Yeah. Using the oscilloscope, I could find.
All right. Okay.
Like, it's not so accurate, but
Roughly lah, huh?
roughly using this method, you can make this code simpler. Otherwise, you have to use another timer to find 100 milliseconds. Okay. The what I did was here I print the real time clock. Real time clock check whether previous second is not equal to the current second. if the previous second is not equal to the current second, it will print the real time clock values. Okay, basically for every 1 second, this function will check whether for every 1 second 10 times this function will check whether real time clock was updated or not. If it was updated, it will print the time. Okay,
Okay.
it's very simple. Like every 10 times in every 1 second, it will check whether time change or not. If it is changed, it will print. That's it. Okay,
Okay.
and then using this one,
Toggle.
toggling the external watchdog time reset pin every 100 millisecond. So I said we must toggle that external watchdog timer pin within 1.6 second. Okay, otherwise that external watchdog timer will reset the reset pin. Right now it will be toggled in every 100 millisecond. It's okay. Understand? Less than
What?
what? Huh?
Okay, try to understand. Yeah.
Yeah, like less than 1.6 second, you must reset that one. So if you can do it every 100 millisecond, it's okay, no problem. That's what is happening here. Okay,
Okay.
so then I make the main loop counter back to 0 here. After that one, it will start from 0 again when it reaches to 4000. So 100 millisecond pass, this will run, again it becomes 0. It goes like that. Okay, understand?
Understand.
Yeah.
Means that it start counting from beginning,
Yeah.
the main loop count.
Yeah. So this is, I don't know other programmers use this method. This is the method I use. Okay, if I don't need exact timing, what I do is I create timing using this other function. So you see, I did not use any other timers. So code is very simple. This will definitely run this function. If the timer got a problem, this will stop running. So which means I am not resetting the external watchdog timer. That external watchdog timer will reset the reset peak if that is the case. Okay, write a very simple line. You understand? Because this thing will definitely run. There are no complicated code to stop this one running. Okay, understand? Can you, is it okay? Can I go to the next one? Can I continue?
Yes.
Okay, sorry. So then we have one function called 24-hour system reset. So this reset peak must reset the entire satellite in every 24 hours. Okay, that's a kind of safety requirement. Okay, so what happens is when time reaches to 000000, this is hour, minute, and second. Reset peak will turn off will turn off every power lines. Okay, then wait 10 seconds. So you can set this one 20 seconds if you want, and turn on again. Okay, if there is a issue in the satellite, all the thing will be resetted again. Let's say someone accidentally sent some wrong command to the satellite, something is start to run. If you have not written any code to come out of that one, so it will keep running. After one day, that will be cleared because everything was resetted. Okay, understand? So let's see this function, how it is done. It should be here. No, I don't remember where. Not here. Maybe it's main pick reset function. Here. So you can see 24-hour system reset. If hour is 0 and minute is 0 and second is 0, first I will print a line and I will print. So in the debug line, you can see this thing happening. Okay, I will print a line saying system is turned off. Okay, so then actually here I don't turn off the buck boost converters. I just disable the OCPs only. That's why I just put only the these OCB disable line. If you want, you can put the correct function like 3.3 off, 3.31 off, 3.32 off, like that. It's you can change if you like. Okay? So here I wait 100 milliseconds and turn off, and 100 milliseconds and turn off. So normally you should not suddenly turn off everything. So that's why I give some delay before turning off. Okay. So using this function, I delay 10 milliseconds. Okay, it's a for loop. Just a for loop runs 10 times, and every time it delay 1 second, and then it print how many second delaying here, and then so before while turning on again I wait at 100 millisecond before turning on the power lines. Okay, you should not turn on suddenly, otherwise those in the circuit there are capacitors, those things will be suddenly charged, so some current inrush can happen. Okay.
Okay.
Yeah. After that one, then system is restarted, and okay, done. That's how it happens. Okay, and then check main pick health. There's a function called check main pick health. So I don't remember where was that function. Let's see, maybe it's here. Okay. Check main pick health. Is 600. Okay. That was it. So there is a counter. Actually, it's a second main. So if you go here in the timer loop, there is a counter called main pick counter and com pick counter. Every time when the timer interrupt happen, it will those two will increase. Okay, it will keep increasing. If no communication happen between the reset pick and main pick, and reset pick and com pick, these things will be keep increasing. Okay, if there is a communication, this value will be resetted back to 0. Okay, let's assume case where no communication happen between main pick and reset pick. So counter will reach to 600, which means 10 minutes. So which means 10 minutes pass. There was no communication. Basically, this function will turn off the main peak and wait 10 seconds and turn on again. So basically that main peak resetting case, okay? Understand?
Yeah, yeah.
So then you will, so when you get the idea, you will understand when you read it, okay? Now you have checked
Yeah.
config here, and if you go to this reset peak config, there is a similar function. It will check whether there's a data coming. If there is a data coming, it will reset the config count. Otherwise, it will reach to 600. Config will be turned off and turn on again. Okay, that's it. Then, so this function check CSAC turn off time to turn off. So this is not valid. This is not for you. It's a different mission happen in the Spartium satellite only. So this function is not for you. Okay, you
Okay.
can just take out.
In bracket take out.
Yeah. Uh, this one. Spartium. You can just make it comment. Okay, if you want. Like if you just do it, it will go. Okay, but you need to remember there is a something can happen now. If you take out this one, what will happen to main loop timing? So I said some time will take to run this one time. Since I take out this function, that time will reduce very small amount. Okay. So which means this maybe this 4000 will not create a 100 millisecond delay. Maybe it will be little bit less than 100 millisecond. It's okay. Okay. Maybe 95 millisecond. This will happen. Okay. Don't worry about that one. Because I reduced the main loop time because I comment this one. Okay. And then we have a function called, okay, before going to communication part between each peak, I will explain how the timer is managed. Okay. So if you go inside the timer loop, if I put this function, this loop will run in every 1 second. So after it happens, we have to load the timer value again using this function. Then we have to update the real-time clock. Okay, let's see how this real-time clock is created. So it is inside this reset peak function. So here, this is the real-time clock function. If second value is less than 59, you have to increase the second value. Okay, else mean 60 case. Okay, second value is 60. You have to make second value 0 again and increase the minute variable. Okay, if minute variable is 60, you have to make the minute variable 60 and increase the hour variable. Okay,
Okay, understand.
if our variable is 24, you have to make it 0 and increase the day variable. Okay.
Okay.
Now,
Okay.
if day variable is 31 and month variable is 4 or 5 or 9 or 11, this is for the 30 days month. You have to make the day variable 1.
But those months only have 30 days only, right?
Yeah, 30 days only.
Okay.
For the 31 days, day value will go to 32. If that is the case, you have to put it back, and it will happen only January, March, May, July, something. Okay,
Mm.
and then there's 1 month you need to write. Okay, if the day is 29
Mm.
and month is 2, that is February. Okay,
Mm.
and especially for the December, you have to do something. You have to, if the day number is 32 and month is December, you have to make day 1 and month also 1. You have to increase the year, because at the that is the year end. Okay, understand?
Yeah, understand.
Can you see something wrong here? It don't have the leaf year option, because in 2024 day value can reach to
20,
30.
30
Yeah,
day value. Month, you mean February?
February, because there is a 29 in the February.
Ah,
So
okay.
at that day, it will go to 30. So you have to put it back to 1. So right now, this is only for normal days, because this, not leap years. This satellite was launched in 2021. There was no, okay, there will be a leap year after 3 years. Okay, I knew satellite will not last that amount. Okay, in the space. I did not want to write that function here.
Ah,
Okay, I can correct this one here right now. About 10 minutes remaining, so I can correct here. And then the way I correct here is, if so, year, where is that one? Oh, my keyboard has an issue, so I need to find the percentage mark. Okay. If you divide this by 4, and if it is 0, I need a variable, something called some char. Char is unsigned int. Okay, so char, let's say leaf year correction. So if so, this function will check whether, if you divide year by 4, if there is a remainder or not. If there are no remainder, leaf year correction is 29. Or else, if there is a remainder, leaf year correction will be 28. No, it should be 30 and 29. So just take this one and put it here. So it is corrected. Okay, I forgot to put the semicolon. So when you get the code, please think how those things are calculated, then you will understand why those values are used. Okay, so this is nothing to do with the RTC, is that mission, say ARC mission. So you can take it out on it. Okay. Okay. Let's go to this settings file. I defined on and off like this. These are the variable used for the RTC and every other functions. Okay. So now let's see the communications between each fix. Okay. So we have reset pick and main pick and com. So we have the TX line, or what, a line from main pick to reset pick, and line from reset pick to main pick, and from pick to main pick, and this one. As example, if you send something in this line, the acknowledgement will come in this direction. Okay.
Okay.
So if you see, come here, there's a function called main to reset array. From main pick to reset pick, there will be some data going. That array maximum size is 20. Okay. Then reset pick to main pick array, that maximum size is 36. Okay. So it can maybe main pick send to reset pick about 10 bytes only. Okay. I just define little bit more byte values. Okay. It doesn't matter. So if I see here, about 9 bytes array comes from 9 bytes command or array. Okay. Array comes from main pick to reset pick. Respond is 36 bytes. Okay. Understand? So
Yes.
Okay.
so I will write this one A, B. There is a format. This A has a format. So here B0 and B1. So the A command will looks like this: 0x B0, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 0. It's not enough space. Can I go write other side, because it will be clear. This one from main to reset pick command or the data. Actually, let's say command or request. So the format is like this: B0, 0x00, 0x00, 0x00. instead of writing this 0x case, I just write only this part B0, 0, 0. These are hex values, okay? Remember.
Okay.
1, 2, 3, 4, 5, 6, 7, 8, 9.
Okay.
This is the normal format. Oh, sorry. End with B1. So I call this one is header. This one is footer. Okay. Reset pick. Check whether this has arrived. Okay. In the pick. So actually that's what it do here. So you can see main to reset array 0th element. It check whether it's B0 and 9th element whether is B1. Okay. Then it will run the function accordingly. Okay. So as an example, if example, okay, I have to stop here now. Can I do in that one in next session?
Yeah, sure.
Yes,
So,
sure.
please remember this is the format
Main to reset.
main to reset. Okay.
Okay.
So without any other byte adding. Okay. This thing will be changed according to the function. Okay.
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 Command 9 bytes. Okay.
So you can change that one easily. So basically you just go here and do this one, but you have to do that change in the main pick also if you do it. Okay.
Okay.
Mm, okay.
Thank you.
Okay.
See you later.
See you later. So wait, what time the next session?
Two. So sorry, wait. 2 o'clock until 4.
Okay.
Uh,
See you. Thank you. Bye.
Thank you. Bye.